evening, everyone. We are in the week 8 problem solving session of the NPTEL course, Control and Tuning Methods in Switch Mode Power Converters. And week 8 is about small signal design of current mode control. I am Teja, a fifth year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. Can you see my screen?
Yes, sir.
So before we start with the current mode control, so what I have planned to discuss today is, so first we'll basically understand the current mode control and how the small signal block diagram will be different from the voltage mode control, and then we'll see the expressions, and then we'll discuss about the model, what type of model we need to consider for the controller design, and then we'll also learn regarding the controller design. So, can anyone tell me, so what will be the difference between the voltage mode control and current mode control small signal block diagram? Or will it be same, or anything will be different, or any idea? Any guesses? Okay. So, irrespective of the current mode control or voltage mode control, the objective is to regulate the output voltage and supply the current that the load is demanding, right? So, in all the controllers, what we basically do is first we'll model the converter, maybe some other device, but first we'll model and then design the controller. So that's why modeling is very, very important. And current mode control basic modeling we have already done in, I think, week 6, where we got the GVC transfer function. So it's the transfer function that will vary. So the GVC transfer function for voltage mode control and current mode control will be different because they are under different controls. But if we draw the block diagram, so the block diagram remains the same. So that's why I have taken this first problem, so that things will be clear. So let me draw. If you have any doubts, you can ask. So is this clear? The small signal block diagram.
Yes, sir.
So in the case of voltage mode control, this will be different. So the different voltage mode control and current mode control. So if you ask in the voltage mode control, GVC will be V naught part up by V con part up, because there the control voltage is generating the duty ratio, and the duty ratio is generating the gate pulse, and then the output voltage is regulated. Whereas in the case of current mode control, we have I reference part up, right? So I reference part up or IC part up. So V naught by IC part up is the GVC transfer function. So both are GVC. So because the control input is different in the case of voltage mode control as well as current mode control, the expression of the GVC will change, but the overall block diagram remains same. So the method remains same, how we have designed for voltage mode control. Similarly, we'll design for current mode control. Only GVC will change. So because GVC will change, the transfer function will change, and the controller requirement will change, and uh, controller gains also will change because things have changed. But the process remains same, and the methodology also remains same. So if we now discuss about the loop transfer function. So what will be the loop transfer function? Anyone? K loop of f?
The
GC
GC into
multiplied by GVC.
GC of s into GDC of s. Yes. So the first thing that is very important while designing the controller is to get the GVC transfer function. And the second one is to design the controller that will meet our requirements like bandwidth and phase margin. So that we have been discussing for quite some time. But the first important thing is how accurate is the model. How accurate is the model. So now today's discussion will be starting with this. So we'll discuss about more accurate model today. So is the audio clear, or are you getting any noise? Because it is raining here. So if you are getting noise, then I can close the door.
It's fine for me, sir.
Sorry,
No, it's fine, sir.
it's fine. So once we get the model accuracy, then we can use the model to design the controller. So if you remember, we have discussed about one model few weeks ago in week 6. Maybe I'll open the notes. So there we have used one model, which is the first order model. So maybe I'll just open so that you can understand what I'm talking about. So this is the week 6. So in week 6, we have discussed about small signal model and transfer functions. But towards the end, I have discussed about current mode control and then the control to output transfer function. So, sorry. So in this control to output transfer function, we have discussed V naught put by IC put, and then we got the equivalent circuit, something like this. So we got IC put and V naught put relationship, which is R parallel 1 by SC. So this is for the ideal and this is for the non-ideal. So you remember this, right? Hello.
Yes, sir.
Okay. So now I'm directly going to take that result and then continue today's discussion. I'll just copy paste from here. So this is the equivalent model, and this is the first order model. Okay. So today's question is write down the expression for control to output transfer function and write down the expression for corresponding poles and loop. So if we take a practical buck converter, even if it has series inductance, because current is flowing through this, the V naught expression is not dependent on RE, but it is dependent on RC, 1 by SC, and R. So can you simplify this expression and let me know what is the GVC expression? I'll also be calculating, but we also solve along with me. I hope you are also solving with me, so we can cross check what we are getting. I can generalize the GBC as something like this. So I can write DC gain KDC into 1 plus S by omega Z, which is 0, by 1 plus S by omega P, which is my force. So now can you tell me the expression of KDC as well as omega Z as well as omega P if you have derived? So I need expressions for KDC as well as omega Z as well as omega P.
ADC equal to R.
Very good. And omega Z?
1 by small rc into C.
1 by small r into C. Yeah, very good. Omega P?
1 by capital R plus small rc into C.
Okay. So now you know that this is for practical. So let me just. So this is for practical work. Considering the variables. If we consider ideal buck, can you tell me what will be the values and how they are going to change? What is KDC? What is omega Z? What is omega? So there is no parasitic.
Small rc is 0. So
Okay,
omega
so
Z will be
KDC will remain same. And what about omega Z?
Infinite.
Infinite, very good.
infinite.
And what about omega P?
RC.
1 by RC.
1 by R. So if omega Z is
sorry.
infinite, the numerator S by omega Z disappears. So there is no 0. So we will not get 0. So there is no 0 in the transfer function. So we will have no 0 in the GBC. Yeah. So this is what we will be getting. No 0 in the transfer function. So if we see the question that I have asked is draw the small signal block diagram of the practical buck converter operating under current mode control, which remains exactly the same as that of voltage mode control. Only the GBC transfer function will be different. So I have also asked what is the expression for the control to output transfer function. In the case of voltage mode control, control input is control voltage, which is compared with sawtooth. Whereas in the case of current mode control, peak current mode control, control input is the current reference, which is compared with the inductor current. Maybe sensed or yeah, it should be sensed. So that's why the GBC expression will vary. And then the important aspect is how accurate is the model. And once we get the model, we can design the controller. So we have already discussed about the first order model. And then in the first order model, we replace the inductor with a constant current source. And then we have obtained V0 perturbation by IC perturbation, which is this expression. So we have to get the control to output transfer function and its poles and zeros. So we got the expression from which we can get the poles and zero locations for both practical as well as ideal buck converter. So is that clear?
Yes, sir.
So if we don't have any queries, we'll go back to the more accurate current mode control model. But before that, I would like to point out few things. So the first order model that we have considered, for the GBC of us. So here we have made few assumptions. So if you remember, we have considered IC perturb is equal to IN perturb, which means we have neglected the ripple. Neglected the ripple. And then also we have not considered any ramp compensation. So if there is any ramp compensation, that is not considered in the first order model. So no ramp compensation. Or I can say ramp compensation is not considered. So considering these approximations, we got first order model. So once we know that these are the approximations that we have considered, now we are going to get a more accurate model. So there are two methods in this model. So first we'll deal with the method one. So now the topic is more accurate current mode control model. SSM is small signal model. So we are going to consider both the ripple as well as ramp compensation, which we have ignored in the first order model. So first we'll start with the method one. Sir has already discussed, but I'll also quickly derive because they are also important for the assignments and your understanding in the future. So I'll quickly derive. Maybe it will take 15 to 20 minutes, something like that, and then we'll solve problems.
Sure,
So
sir.
in the method one, so let me first draw the diagram. So whenever we say ramp compensation, so you need to keep this in mind, ramp compensation. So this is like a ramp. So either this can be added to IL or subtracted from IREF or IC, whatever we are calling. So it is a ramp compensation. So whenever we want some ramp compensation, so one of the reason is when the system is unstable, we add ramp compensation to make it stable. So when we do that, we either add it to the inductor current or subtract it from the I reference. So here in this analysis, we'll subtract it from the I reference. So previously, we had I reference. Okay, now we'll have a ramp compensation. With that, this is my IC because now we are subtracting from the previous constant. We are subtracting the ramp. So that's why it is falling like this. So this is my IC. So this is my IC. Okay. So now it is being compared with the inductor current. So this is my IC. So this is our previous IC. Now this is IC minus ramp compensation. So this is IC minus ramp compensation. So the ramp is subtracted from this. So now we are going to compare it with the inductor. So let's say inductor starts from here, hit it, and then come back. Similarly, hit it, and then come back. Then hit it, and then come back. So this is how the steady state waveform looks like. So let us assume the slopes are M1 and minus M2. And then let us assume the ripple is delta M2. Okay. So now let us assume the slope of this is minus MC. So now you know this is the overall timing diagram where we have not ignored the ripple Also, we have considered the ramp compensation, which were not there in the previous original first order model. So now we are going to calculate the average of the inductor current. So in order to get the average, we know that for a triangle waveform, the average passes through its midpoint, right? Agree, everyone? The average passes through the midpoint. Everyone agree?
Yes.
Yes. So in order to get to the midpoint, first we need to find this point. So we need to find this point. So we know that this is the on time, which is dt. So now I can calculate the I peak of the inductor, say I peak, which is nothing but IC minus MC into dt on time, because IC is this. So this is my IC peak and the inductor peak is IP. So it is falling with a slope of MC for a time of how much for a time of dt. So my I peak is nothing but IC minus MC into dt. So is this clear?
Yes, sir.
Okay. So now,
Sir, there will be
yes,
minus delta IL by 2 also will be subtracted, right? To get
yes,
that.
yes, I'm coming to that point. So this is the I peak.
Okay.
So now if I discuss about the average of IL, it is the midpoint of the triangle. So I need to come from this point to this point. So the height is delta IL. So this height will be delta IL by 2. So this height and this height both are equal and they will be delta IL by 2. So now if I calculate the average, so my average IL is nothing but I peak minus delta IL by 2, which is IC minus MC into dt minus delta IL by 2. So is this clear?
Yes, sir.
Okay. So now, if I want to write delta IL in terms of M1 and dt, I can write delta IL is nothing but M1 into dt, right? So if I consider the triangle, this is dt, this is M1, and this is delta IL. So I know that delta IL by dt is equal to M1, right? So M1 into dt. Agree, everyone?
Yes, sir.
So now, if we do that, I'll get the final expression as average of average of IL, and say IC is also like average minus MC into dt minus M1 into dt by 2, right? So now if we do the perturbation, we'll get IL plus IL perturbation equal to IC plus IC perturbation minus MC plus MC perturbation into MC, say MC perturbation is not there, say MC is constant. So because MC is fixed, right? So MC is not changing. So we'll have only perturbation in the duty ratio. So MC into D plus D perturbation into T minus M1 plus M1 perturb into D plus D perturb whole into T by 2. Agree? I have perturbed everything and MC is constant because MC is in our hands. Whereas the slope M1 can change because it depends on V0. So V0 is not always regulated, right? During transient, it is changing, but MC is fixed. So that's why MC perturbation is not considered. MC perturbation is 0 because MC is always constant. Is this part clear? Hello.
Yes, sir.
Okay, sir.
Okay. So now, because we are doing AC analysis, we need the transfer function, right? So we are doing AC analysis. So we'll remove the DC terms because DC terms are considered for DC analysis. So we'll remove the DC terms. Also, we know that we ignore second order term. So when two perturbations are multiplied, that we ignore because it's a first order approximation. So we ignore second order term. So now we will get IL perturb equal to IC perturb minus MC into D perturbation of D minus M1 perturb into capital DT by 2 minus capital M1 into D perturbation of T by 2. Agree?
Yes, sir.
So now if I want to find D perturbation, so let us bring D perturb here. So D perturb is equal to MC plus M1 T. So MCT, or let me check out the T also. So D perturbation is MC D perturb into MC plus M1 by 2 into T is equal to IL perturbation minus DT by 2 into M1 perturbation. Agree?
Sir, is it IC perturb minus IL?
Yeah. Sorry. Yes, yeah, thanks for correcting. So this is IC perturbation minus IL perturbation minus DT by 2 into M1 perturbation. Right? Is this clear till this point?
Yes, sir.
Okay. So now if I want to generalize in this format, say D perturb is equal to FM into IC perturb minus IL perturb minus K1 into Vn perturb minus K2 into V0 perturb. Say I want to generalize in this format. So how can I write this? So first of all, I have to bring the constant on this side, right? So I will get D perturb equal to 1 by MC plus M1 by 2 into T multiplied by IC perturb minus IN perturb minus K1 into Vn perturb minus K2 into V0 perturb. Agree? Agree, everyone?
Sir, M1 perturb.
Yes. So I will have to, yeah, okay. You are right. So minus dt by 2 into M1 perturb, right? Is this clear from this step?
Yes, sir.
Okay. So now what I will do is, we know what is M1 for a buck converter. So I'll expand this. So minus dt by 2 into M1 perturb is equal to minus dt by 2 into V in perturb minus V0 perturb by L, right? In buck converter, M1 equal to V in minus V0 by L, right? For buck. So I can write this expression, right?
Yes, sir.
So now if I expand, I'll get minus dt by 2L into V in perturb minus plus dt by 2L into V0 perturb. So now this becomes my K1 and then this becomes my K2. So minus K1, so K1 will be d2 by 2L and K2 will be minus d2 by 2L. So if I take minus comma, So if I take minus common, because it is minus K1 minus K2. So if I take minus outside, I'll have right. So I have taken minus outside. So it is dt by 2L into being part of, because here it is minus K1 minus K2. So I have taken minus common. So K1 is dt by 2L and K2 is dt by minus dt by 2L. So let me quickly summarize so that if you have any confusion, it will be clarified. If you have further questions, then you can ask me after I summarize. So where we have started is we have previously considered a few approximations and then we got the model. But what if we do not consider those approximations, which are this one? IC part equal to IL part, which means we have neglected the variable. Also, we have not considered any type of ramp compensation. So now we are going to consider both. So after removing the ramp compensation from the I reference, this is red color waveform is what we actually get, which is the actual reference, which is then compared with the inductor current. So now, if you see, this is my IC. So the peak of the inductor current is IC minus MC into DT because this is on time. So this is the peak. So now the average of the triangular waveform is the midpoint, which is peak minus height by 2. So average of IL is peak minus height by 2, delta IL by 2, and delta IL can be written as M1 into DT. So now we get this expression. After that, we have perturbed and considered only AC terms because we are doing AC analysis. So we'll remove all the DC terms. Also, we'll ignore the second order terms because in this we'll get 4 terms. One is the DC term, one is the second order term. So both are gone. So we'll get 2 terms from here, 1 term from here, 1 term from here, 1 term from here. After that, we have simplified into this expression. But if we want to write it in this form, which is a generic form, then we have further simplified and then we got FM as 1 by MC plus M1 by 2 into T, K1 as dt by 2L and K2 as minus dt by 2L. So is this clear until this point?
Yes, sir.
Yes, sir.
Okay. So others, if you have any questions, you can ask as we'll proceed to method 2.
Sir, it is K2 is minus dt by 2L, right, sir?
K2 is minus dt by 2L, yes. So K1, okay, maybe I'll write it. So FM is 1 by MC plus and 1 by 2 into T. And K1 is dt by 2L. And then K2 is minus dt by 2L. So these are the constants that we'll be getting. Right?
Yes, sir.
So if you don't have any queries, then we'll proceed to method 2. So method 2 also I will consider the same diagram. Method 2. So in the case of method 2, what we'll be doing is we'll not consider the average of this entirety. Instead of that, what we'll do is we'll consider the average of this plus we'll consider the average of this. And then we'll take the overall average. Previously, what we have done is we have considered the average of the entire triangular and we have calculated the midpoint. So now we calculate the midpoint for the left portion as well as the midpoint of the right portion. And then we'll consider the overall average. So why we are doing this is because now we will further consider that we want in terms of M1 as well as M2. Because previously in a single cycle, we have considered, okay. Uh, so now Wonderful. So now let me read right. So the waveform remains same. Here, if you see, we have considered the average as peak minus height by 2. But we have not considered any expression in terms of M2. But now what we are going to consider is we want the average to be on the left hand side plus the average on the right hand side. Then we'll consider the overall average. So now what we are going to do is first we are going to calculate the average on the left side and then we are going to calculate the average on the right side. So we know the I peak expression. So I peak is IC minus MC into dt by 2. This you know. So now if I want to calculate, I want to calculate the average on the left side as well as average on the right side. So for that what I'm going to do is I need to calculate the midpoint on this. So I will calculate this midpoint. Also I'll calculate this midpoint and then I'll take the overall average. Say this is my I1 and this is my I2. I know that I1 is nothing but IC minus MC into, sorry, this is not dt by 2, this is just dt. So MC into dt minus M1 into dt by 2. Agree? How I am getting the midpoint I1? This I peak minus delta IL by 2. So I can write delta IL as M1 into dt. So this is just same as what we have gotten here. IC minus MC dt minus M1 dt by 2. So is this clear? I1. How we are getting I1? First of all, there is less than a minute. If this meeting ends, kindly join back. So is this clear or do you have any confusion? If you have confusion, please let me know. Any doubts until this point?
Same as
No.
first method, right, sir?
Yes. So same as first. So I1 is what expression we have gotten in the method one. But previously, what we have considered is the average of IL we have considered as I1. But now we are not going to do exactly. We'll do it slightly different. So we'll also calculate I2. So I2 is nothing but IC minus MC dt minus M2 into 1 minus dt by 2. So you know that we have the inductor current like this. And we have the slope here M1 and we have minus M2. And you know this is dt and this is d prime t. So we know that delta IL is equal to M1 into dt, which is also equal to M2 into 1 minus dt. So although it is equal, now we are writing in terms of M2. So I2, I am going I peak minus M2 into 1 minus dt by 2. Whereas I1, I have written I peak minus M1 into dt by 2. So is this clear? This step, both the terms, how we have gotten I1 and I2.
Yes, sir.
So now what we are going to do is, now we are going to consider the average in terms of I1 and I2. So I1 is there for dt time, I2 is there for 1 minus dt time. So we'll get I1 average of IL is nothing but d into I1 plus 1 minus d into I2. Because there is a ratio d for this and 1 minus d for this. So now if we do the same and then simplify it, we'll get average of IL equal to d into average of IC minus MC dt minus M1 dt by 2 plus 1 minus d into average of IC minus MC dt minus M2 into 1 minus D by 2, right? So now if you see, these terms are same in both the expressions. So we can segregate them and write something like this. Average of IL is equal to IC minus MC dt. If we write the other terms, we will get M1 into D square T by 2 minus M2 into 1 minus D square T by 2. So this is what we have gotten, which is slightly different from what we have gotten in the method one, because in the method one, we have only considered this midpoint as the average. So we got this midpoint. But what if during this M2 may also can change it? It can be in transition. So we have considered the average on the left part plus average on the right part. And then we have considered the overall average. So that's why we have multiplied by D on the left side and 1 minus D on the right side. And then we have considered the overall average. So is this clear?
Yes, sir.
Okay. So now, because we have done the averaging in the previous case, the same thing we can do it here as well. So if we do that, we need AC, right? So we are doing AC analysis. So I can directly consider the AC part. I'm not considering about the DC. I'm not considering about the higher order term. So I'll directly consider the AC parts. So we'll get IL factor is equal to IC factor minus MC is constant. So MC into P part of T. And here we'll get two terms, one for the M1 part of, another for the D part of. So it is minus M1 part of into D square T by 2. And then for D part of, we have to differentiate it, right? So you know this Taylor expansion. So if we have f of say x function, and if you want to linearize it, we'll do dou f by dou x into kind of x part of, right? And then dou square f by dou x square. So first of all, right, we have f of x naught, f of x. We'll write it as f of x naught plus dou f by dou x into x minus x naught plus dou square f by dou x square into x minus x naught whole square plus up to 7. So this f of x is this f of x, and f of x naught is DC term, and then these are all higher order terms which are represented, which are neglected. So these are neglected because they are higher order terms, and x minus x naught is like x tilde. So that is the x perturbation. So what we are doing is we are removing the DC parts because we are bothered about AC analysis, and all the higher order terms we are ignoring. So now if I want D perturb, so this is my f of x. So now I want D perturb. So D perturb term I want to get. So what will I do? I will do dou f by dou D. So if I differentiate it with D, then what will I be getting? I will be getting minus M1 into dt into D perturb, right? So this is my first order differentiation at the equilibrium point, which is minus 2m1 into dt by 2, 2 get cancelled. So m1 into dt into this D perturbation. So that's how I get the D perturb. So is that clear? Or do you have any confusion? Is that clear?
Yes, sir.
Okay. Similarly, for the M2 part, we'll get two terms. One is minus M2 perturb. Again, this should be capital D. So this is D square into D. Here M2 perturb into 1 minus D whole square into T by 2. Again, if we take the differentiation, then we will get 2 will get cancelled. So m2 into 1 minus dt into minus 1 whole into d part of. Agree? So I have taken differentiation with respect to d. So 2 will get cancelled. M2 is M2, 1 minus d. And again, I have to differentiate the inside term, which will give me minus 1. So this is the overall term that I am getting. Any confusion or is it okay? If you have any confusion, please let me know so that I'll explain again.
No, sir, it's clear.
It's clear, okay. So others, if you have any doubts, you can ask. I'll proceed further. If you have any like minute confusion also, don't hesitate, you can ask. So I'll explain, then we'll proceed further. Okay. If you don't have any questions, so then I'll segregate this. So we have IL putter is equal to IC putter minus MC into. So if I take deperturbation common and minus also common, so I'll have minus of MC into T plus M1 into dt minus minus. So minus I'll have M2 into 1 minus d into T whole into d putter minus d square T by 2 into M1 putter minus 1 minus d whole square into T by 2 into M2 putter. Right? I have segregated d perturbation terms inside this, which are this term, and this term. So there is minus minus, so this becomes plus. So I have taken minus common, so this will have 1 minus. This minus I have taken common, so here I have plus, here also I have plus. Okay. So now if you see, I have written here one thing. So at steady state, m1 into dt is equal to m2 into 1 minus d into t. So at steady state, the height remains same. So both of them will be equal. So with that, I can consider these two are cancelled. So now we will get IL pattern is equal to IC pattern minus MC into T into D pattern minus D square T by 2 into M1 pattern minus 1 minus D whole square into T by 2 into M2 pattern. So now if I want to write D pattern expression, I will write D pattern is equal to 1 by MCT into IL pattern minus IC pattern minus D square T by 2 into M1 pattern minus 1 minus D whole square into T by 2 into M2 pattern. Clear? Again, if I want to generalize in this form, then this will be my Fn. Now I have to find K1 and K2. So now what I will do is I will consider minus d square by t into m1 perturb minus 1 minus d square t by 2 into m2 perturb. So we know that in a buck converter, m1 is nothing but v minus v0 by l and m2 is v0 by l. Slope. So we'll substitute it here. Then I'll be getting minus d square t by 2 into v in perturb minus v naught perturb by l minus 1 minus d whole square into t by 2 into v naught perturb by l. So my v in perturb coefficient will be minus d square t by 2l into v in perturb, and if I take minus comma, or let it be, if I take v naught perturb by l common, then I'll get d square minus 1 minus d whole square. Right. So if we simplify this, what we'll be getting? We'll be getting 2d minus 1, right? So this is 2d minus 1. So if I rewrite it in a different way, then I'll get minus of d square t by 12 into v in perturb plus 1 minus 2d into v naught perturb. So this will be my k1, this will be my k2. So now if I write the expressions, fm is how much we are getting? I was getting 1 by mc into t. Similarly, I'll get k1 equal to d square t by 2h, and k2 I will get 1 minus 2d by t is there. So I have forgotten to write t. So here we have t. Here also t. T by 5. Let me quickly summarize, so then you can ask if you have any queries. So in the method 2, what we are doing is we are not assuming that I1 and I2 are same. So we are assuming that I1 and I2 are different. And then we are calculating the average here and then the average here. Because we are assuming that the slope may change after this. So it may not be like a triangle like this. So what we are assuming is basically we are assuming that the triangle can be something like this. So during transient. So in that case, how do you calculate? We'll calculate the average of this region, and then we'll calculate the average of this region, and then we'll calculate the average of both, which is what exactly we are doing here. So we have calculated the midpoint of this, we have calculated the midpoint of this, and then we have taken the average. So the midpoint I1 is nothing but IC minus MC dt minus M1 into dt by 2, and I2 is nothing but IC minus MC into dt minus M2 into 1 minus d by 2. So now the average of the current is d into I1 plus 1 minus d into I2. And then after simplifying it, we got this expression. Now for AC analysis, I'm only considering the AC perturbation. So once we do the AC perturbation, these two will be cancelled because at steady state, this height is same for both. So M1 into dt is equal to MT into 1 minus d into t. So we are getting this final expression. If I want to generalize in terms of V in perturb and V not perturb, then I have to further simplify. And after simplifying, these are the constants I am getting. So now if I want to compare both method 1 and method 2, so both are like, so this I am comparing this method 1 with now method 2. So for method 1, So this is for method 1 and for method 2. So this is the overall discussion about the different type of models that we can use for current mode control. So any doubts until this point before we go for the design part?
Sir, just from the exam perspective, is it like you would prefer us to memorize this because like it will not be feasible to derive all this during the
Yes,
exam,
yes,
sir?
yes. So in that case, you can just remember the final results, or you can take it in a notes and if you derive it by yourself, then you should be able to derive quickly. But I would suggest, because the derivations are lengthy in this case, you can directly remember the final expressions. And this MC will be captain, so this MC is not small because
Okay, sir. And sir, in the assignments, we have direct questions like these, like what is K1, K2 values.
okay.
From the exam perspective, we can get questions like place the values, like actually find out K1, K2 by giving the D values, L values if it is
Yes,
given.
yes.
Those sort
So
of
that can also be done. Yeah, you're right. So
fine.
they can ask for this buck converter at steady state, what is FM, what is K1, K2. So you can calculate the duty ratio, and then you can calculate TL, and then you can.
Fine, sir. And final question, that this values, it will hold same for buck boost for both. It will hold the same, right?
No,
These values.
because if you consider boost, then the slope M1 will be different, because here I have considered, sorry. So if you see here, I have considered M1 equal to V in minus V0 by L. In the case of boost, it will be V in by L. So in that sense, the expressions will vary. So till here, we have not considered any buck or boost. From the waveform, we got this expression. But once we substitute M1 and M2, so those terms here also, this is for buck. In the case of boost, it will be V in by L and V0 minus V in by L. So the final expressions will vary slightly. And yeah, the duty ratio term also is not same. Here D is V naught by V in, there D is 1 minus V in by V0.
Oh, okay.
Apart from
Because I
that,
don't
everything
remember
remains
seeing
same.
any separate expressions for boost. That's why I was
I
just
think sir has not
mm,
discussed. So as far as I know, if he has not even discussed or mentioned any result, I think then in that case, that may not be asked. But you can quickly derive. All you have to do is you have to substitute the M1 and M2 values for boost converter, and then you will get similar expression for boost as well. Only from this part you have to do. Only this expression will remain, will be different. So M1 is, if we write, so for boost converter, M1 is V in by L, M2 is V0 minus V in by L. So then it will be slightly different. So here you will get different K1 and K2, but almost same length. Until this point, it is same. Only if you want to write in terms of V in and V naught, it will slightly vary. So I think that will be easy. You should be able to derive. Just substitute this and simplify it.
okay, sir.
So if you have any doubts till this point, you can ask. Else we'll solve a couple of problems quickly. Okay. So if you don't have any questions, then we'll quickly solve design problems. So in the first question, I have asked, consider an ideal buck converter under current mode control with the following specifications. So V in is 10 volt and V naught is 0.8 volt. Inductance is 150 nanohenry. Capacitance is 1 millifarad. Resistance is 0.05 or 1 by 20. And switching frequency is 1 megahertz. So now I'm asking you to calculate the steady state duty ratio, calculate the poles and zeros of GVC of S, and write the control to output transfer function, and which type of controller is needed to control this converter. And also, if we are targeting a bandwidth of FSW by 10, then design the controller and obtain the controller gains. So I'm giving you like some time to solve. So I think you should be able to calculate the first part easily. So what will be the answer for A?
0.08.
0.0. Very good. So the steady state duty ratio will be 0.08. So now solve B. Once you solve, you let me know. Then I will also solve. Then we can cross check the answers. Then we'll move to C. Then we'll move to D. Then we'll move to E.
So there will be no zeros, right? Like buck converter plus ideal, so zeros
Yes,
should
yes.
not be
So
there.
there is no zero. Yeah, you're right. So because it is ideal buck converter, there is no zero. Or I can say that omega z is infinite. So has anyone calculated pole?
20,000.
20,000. Okay. So if we go back, we know that for ideal buck converter, omega p is 1 by RC. So let us calculate omega p. So omega p is 1 by RC and R is 0.05 or I can say 1 by 20. And capacitance is 10 to the power minus 3. So it is 20,000. Yes, you're right. So omega p is 20,000. Okay, so now if we want to write down the control to output transfer function, so what will we be writing? GVC of S, anyone?
R by 1 plus S by omega P.
Yes. So R is 0.05. So I'll write 0.05 by 1 plus S by 20,000. Okay.
Sir, one doubt regarding
Yes.
previous one.
Okay.
Suppose value of pole has to be entered in a numerical data entry type question.
Can
So
you
do we
please
have to
repeat?
enter, suppose the question is that numerical data
Okay.
entry type, we have to type in the value.
Yes.
So when value of pole, is it 20,000 or minus 20,000? Actually, it is at minus 20,000, right?
Yes. Yes. So it's actually not also minus 20,000 because if you see the pole location is minus omega p, but like yeah, you are right. If I ask what is the pole, it is minus 20,000. But in the question, they will ask what is omega p. So omega p will be 20,000. So you are right. So here the pole location should be actually minus 20,000. But pole location is not omega p. Pole is at minus omega p. So omega p is 20,000 and pole location is minus 20,000.
Okay, okay, sir.
So here zero location is at minus infinity because it is like a LHP zero. So here the pole location is at minus 20,000. Yeah, thanks for pointing this out. But if you see any question where they ask pole and if the answer is given positive, kindly let us know. As far as I remember, there is no such mistake done. But in case if we uh, overlook at it and if there is any such mistake, kindly report to us. Then we'll rectify it. Okay, so this is GVC of S. Now, which type of controller is needed to control this converter? So, depending upon how sir has previously designed the controller, so which controller do we need? Proportional controller, PI controller, PID controller, or how is this decided?
The controller will have a 0 to cancel this pole.
Okay.
Then one integrator.
Okay. So then, what type of controller it becomes?
PI controller.
PI controller. Very good. So zero, we need zero to cancel the pole. And we need integrator or one base. To achieve zero steady state error. Also, we'll be needing some DC gain so that we can set the gain crossover frequency to achieve the required gain crossover frequency. So based on the requirements, it will be PI controller. We'll see how it becomes PI controller. So in you know that in a PI controller, we have GC of S is KP plus KI by S. So if you write like this, you will get KPS plus KI by S. So if I take KI common, KI by S into 1 plus S by omega controller 0, where omega controller 0 is given by KI by KP. Clear?
Yes, sir.
So instead of solving it numerically, I will solve it in a generic way so that we can correlate with any problem. So I'll write in terms of omega p and omega z. So yeah, so my GVC of S is nothing but KDC by 1 plus S by omega P. And my GC of S is Kc controller gain by S into 1 plus S by omega Cz. So now what is my loop transfer function? K loop of S, anyone?
KDC into KC by S.
Yes. So if we actually write, we'll get KDC into Kc by S. Actually, these two terms are also there, but because of whole zero cancellation. So this is cancelled to this. So from this, we'll get one equation, which is omega Cz, which is Ki by Kp equal to omega P. So we need two equations because there are two unknowns. So first equation is this, which is Ki by Kp is equal to omega P. Okay, so this is my equation one. So now my K loop of S becomes KDC into Kc by S. So now how to get another equation? From where will I get the other equation?
Gain crossover frequency is given
Yes.
1/10 of
Yes. Very good. So we can get from the gain crossover frequency. So gain crossover frequency, how will we get? We know that K loop of S at S equal to j omega C, the magnitude will be 1. So 1 equal to KDC into Kc by omega C. And what is actually Kc? Kc is nothing but Ki, right? So Kc is Ki. So we can get Ki is equal to omega C is what? 2 pi Fc by KDC. So Fc is up to the user's choice. It can be anything. So I'm writing in a generic fashion. So omega, it can be FSW by 10, FSW by 20, FSW by 8. So it's user's choice. So Ki is 2 pi into Fc by KDC. Clear so far?
yes, sir.
So now you have two equations, two unknowns. So now can you quickly calculate for this question, what is my KPK? So first of all, which type of controller is needed? We need PA controller. It should be sufficient time. Okay, and now we need to design the controller targeting a bandwidth of FHW by 10 and switching frequency is 1 megahertz. So we are targeting basically 100 kilohertz. So targeting 100 kilohertz for this transfer function, quickly calculate the gains and then we'll cross check.
Sir, Kc value is 12.566 into 10 power 6.
How much is your KC that you are getting?
12.566 into 10 power 6.
And KC is nothing but Ki. So this is Ki. So if you have not calculated KP, calculate KP. In the meantime, I will calculate KI. So KI is 2 pi into FC is 100 kilohertz. So 100 into 10 to the power 3 by KDC is 0.05. So let me calculate. I hope others are also able to calculate. Just let me know if you are getting the same answer or not. So how much is the answer that people are getting for KI?
12.566 into 10 power 5.
5 or
10 power
6? 6, right?
6.
Yes. 12.566 into 10 to the power 6. Now, whatever the meeting might end, there is less than a minute. If the meeting ends, kindly join back so we can continue. So, anyone, what is the value of KP?
628.3.
628.3. Let us check. KP is KI by omega p. If this meeting ends, kindly join back. Let me calculate.
Yes, sir. 628.3.
Yeah, 628.3. Can you see my screen?
Yes, sir.
Okay. So, the gain that everyone is getting is 628.3. Okay. So now that in this question, I have given an ideal buck converter, which is operating under current mode control with the specifications. And then I have asked calculate the steady state duty ratio and calculate the poles and zeros of GVC of S and write down the control to output transfer function and the type of controller that is needed and how to design the controller. So we have calculated the duty ratio simply. And then we have calculated the poles and zero location. There is no zero, or I can say the zero is at minus infinity and pole we have calculated. And then we got the transfer function. And then we have seen that PI controller is sufficient for this. And then we have designed the controller targeting a certain bandwidth. And if I ask you what is the phase margin for this controller, how much is the phase margin? Like
90 degree.
Yeah, 90 degrees because it is 1 by S. So phase margin is 90 degrees. So the phase margin is 90 degrees. So it is overdamped, and which is what Sir has shown in his lectures that the response will be overdamped. So is this clear until this point?
Yes, sir.
Okay. So now let us go to another question. Let me read it out for you. Consider a practical buck converter under current mode control with the following specifications. Vin is 12 and V naught is 1.5. Inductance is 120 nanohenry. Capacitance is 1.2 millifarad. R is 0.1. Switching frequency is 700 kilohertz. On resistance is 2 ohm. DCR of the inductor is 10 milliohm and ECR of the capacitor is 1 milliohm. Calculate the poles and zeros of GVC of S. Write down the control to output transfer function. Which type of controller is needed to control this converter? Design the controller targeting a bandwidth of FHW by 8 and calculate the corresponding phase margin. So I'm giving you some time. Calculate the poles and zeros of the transfer function and then we'll write the transfer.
Sir, omega ESR is 8.33 into 10 power 6.
Omega ESR is 8.33 into 10 to the power 6. And omega P?
8,250, 8250.82.
So I hope others are also calculating. Let me just take the expression from here. So this is omega Z and omega P, and KDC is R. So this is the omega Z and omega P. Okay. So omega Z can be obtained as RC, which is how much? 1 milliohm, and C is 1.2 millifarad. So 1 by 1.2 into 10 to the power minus 6. Right? One is milli, another is milli. So 1 by 1.2 into 10 to the power minus 6. So I can say that 1 by 1.2 into 10 to the power 6. So it is 0.833, right?
Yes, sir. It's 0.833 into
Okay.
10 power
So
6.
this is
Yes, sir, 0.8.
0.833. So now if I right, so omega z is 0.833 into 10 to the power 6. Similarly, if you calculate omega p is 1 by r plus rc. R is how much? 0.1 and RC is 1 milli. So we'll get 1 by 0.101 into 1.2 into 10 to the power minus 3. So we'll get 1000 by 1.2 into 0.101. So we'll get 1000 divided by 1.2 into 0.101. 8250.82. Yeah, so this is correct. So omega p is coming 8250.825. So is this what everyone is getting? The expression for both?
Yes, sir.
Okay. So now what will be the transfer function? GVC of S? What is KDC?
0.1.
0.1. So we'll get 0.1 into 1 plus S by omega ESR is 0.833 into 10 to the power 6. And in the denominator we have 1 plus S by 8200.825. This is the overall transfer function that we are getting. So poles and zeros, poles will be minus 8250.825 and 0 is minus 0.833 to 10 to the power 6. We have also written the controller transfer function. So which type of controller is needed to control this controller? Sorry, control this converter. Any idea? Anyone?
one controller will have one pole at origin, then another pole to cancel that ESR 0,
Okay.
then one 0 to cancel this pole.
Yes, very good. So let us go step by step. So we need to have one 0 and also one pole, and then we need to have one integrator. And also we'll have DC gain. So why 0 to cancel Grant's pole? And why 1 pole to cancel plants 0? Integrator to achieve 0. Reduced power. DC gain to achieve desired bandwidth or gain performance. So overall, what type of controller is this? Anyone?
Type 2.
Yes, very good. So this is type 2 controller. And if I write the controller expression, so it will be GC of Z is equal to, say, controller gain KC into 1 plus S by omega C Z by S into 1 plus S by omega C. So now let us not do it for this question. Let us do it for a generic case. So this is my GC of Z. This is my GBC of Z. Okay, so now what will get cancelled and what equations will we be getting? Hello. What will be cancelled with what?
That omega, that Z on top will get cancelled with omega P.
Yes. So if I use this numerator will be cancelled with the denominator, and this numerator will be cancelled with the denominator, giving us two equations. One is omega CZ is omega P, and omega controller pole is omega Z. So now what is K loop of S?
KC into KDC by S.
KDC by C.
Very good. So how many unknowns are there and how many equations do we need?
Three variables are there so far.
Okay.
Two.
So
So
how
far
are
two
we going to
equations.
get the third equation?
Gain crossover frequency.
Yes,
That
gain
expression.
crossover frequency. So if you remember, we can directly write. So we'll get 1 equal to Kc into Kdc by omega C. So we need Kc. So Kc is nothing but 2 pi Fc by K into Dc. So these are the three unknowns that we need to get the or to design the controller. So now let us get back to the question. So I hope you have written down these number. So now design for this controller. So design or calculate all the gains and note that the bandwidth here is FSW by 8 and FSW is 700 kilohertz, not FSW by 10, but FSW by 8 and FSW is 700 kilohertz. So I'm giving you 5 minutes time to calculate all the gains, and whoever has calculated, let us know. Then we'll cross check.
Sir, here also omega c is 1/10 of switching frequency.
Here 1/8 of the switching
1/8.
frequency, and
Okay.
switching frequency is 700 kilohertz. So has anyone calculated?
Kc is 5.49 into 10 power 6.
Right. KC is
5.49
okay.
into 10 power 6.
Okay. And omega C Z and omega CP. How much is omega CZ?
omega CZ equal to omega P.
And how much is the value? 8250.825, right? 8250.825. And omega CP is 0.8333 into 10 to the power 6. Well, because I have not calculated, let me quickly calculate Kc. So we'll get Kc is 2 pi by KDC is how much? R, right? R is 0.1. And this is switching frequency 700 kilohertz by 8 because I have given that as my design requirement. So let me calculate 2 pi into 700 into 10 to the power 3 by
Sir, is it 700 or 7,000?
700 kilohertz. 700 kilohertz. 700 into 10 to the power 3. Is that clear?
Yes, sir.
So if I write also 10 to the power minus 6. I'm getting 0.549 into 10 to the power 6. Can anyone please confirm? Can anyone please confirm? KC, I'm getting 0.54 into 10 to the power 6.
So I got 5.49 into 10 power 6.
Okay, sorry, I forgot 0.1. You were right. 2.1, right? Okay. Sorry, my bad. 5.4. Okay. So now if I write the overall GC of Z, I'll get GC of Z is equal to 5.49 into 10 to the power 6 1 plus S by omega Z is 8250.825 by S into 1 plus S by 0.833 into 10 to the power 6. So this is the controller that we have obtained for the practical buck converter that was given and for whatever they have asked. So if you see like this pole is far away from the imaginary axis. So this is coming because of the ESR. Say ESR is very, very small, that it is too far away from the imaginary axis. And say if this is neglected, then type 2 will become PA controller. Because we are getting one additional pole in type 2. Say if this pole is too far away that it can be ignored, then it will become PA control. So if we go to the last part of this question, calculate the corresponding phase margin. So how much is the phase margin? Anyone?
90 degree.
90 degrees, very good. So phase margin is 90 degrees. So this is the last question. Just to quickly summarize what we have discussed in the last question, I have given a practical buck converter operating under current mode control, and then I have given different parameters, and I have asked calculate the pole zeros as well as control to output transfer function, and what type of controller is needed, and how to design the controller for a bandwidth of FSW by 8, and the corresponding phase margin to be calculated. So we know for a practical buck converter, the poles and zero locations are given by this, which we have discussed at the beginning of today's lecture. And then I have calculated the locations. And then we also know the DC gain. From that, I got the GVC transfer function. So now depending upon these poles and locations, we have seen what are the requirements of the controller. And based on that, we got it's a type 2 compensator. So now if we do the stable pole zero cancellation, we got these two equations for both unknowns, and from the bandwidth we got the third equation to calculate the third unknown, and then from this we got the three unknowns for the controller targeting a bandwidth of FHW by 8. So this is very important. Not always you are asked to do for FHW by 10. Sometimes they can twist the question and may give a different bandwidth. So based on that, you have to take a decision and calculate it accordingly. So we got the overall controller. And then this type 2 can also become PI controller if this is too far away that it can be neglected. And then we have seen the phase margin is 90 degrees in both ideal as well as non-ideal buck converter operating under current mode control, because all the poles and zeros are getting cancelled. Unlike voltage mode control, we don't have any additional pole to tune bandwidth as well as phase margin, because we are doing the pole zero cancellation. All the poles and zeros are cancelled and we are left with the integrator. So if you have any queries, you can ask, else I will quickly summarize today's session, and then I will end this session.
Sir, typically for a system, like,
Yes.
is it preferred to have high gain, high DC gain or lower DC gain, or it is purely just to set the phase margin where we want it, sir?
The DC gain of the controller.
Yes, sir.
Yeah, so it is not like preferable, but too much gain may be practically not implementable. So the DC gain is basically coming from the bandwidth. So what happens is, if we go to this equation, so the gain of the controller is proportional to the bandwidth. Say theoretically it is possible to get certain bandwidth, but practically there can be many other dynamics, and there are many other issues which are not covered in this course that may put a limitation on the gains, the gain of the controller that can be implemented. So in that case, what happens is we need to go for a reduced bandwidth. So we need to go for reduced gain. So too much high gain may be practically not implementable. So in such cases, we need to reduce the bandwidth so that the controller can work. So if the gains are too much, it may lead to instability under certain cases, like if you consider digital control. So the digital counter, like the digital part or the digital implementation, will pose some limitation on the bandwidth that we can achieve, and it can cause instability. So in that cases, very high gains are not implementable and the system may not be stable under such cases. So in that case, we need to go for reduced bandwidth. But yeah, theoretically, we are basically dealing with all theoretical calculations. So there is no such issue in theory. As well as in simulation, it will work, but hardware will have additional, like delays, op-amp delay, and then op-amp saturation. So if you have high gains and op-amp saturation is like limited, so op-amp might get saturated and converter may become unstable. So yeah, because if you see in simulation, there is no saturation, right? The control output, VCon or IC, it is basically coming out of an op-amp. In the case of simulation, there is no upper and lower limit, but in the case of practical hardware, there is upper as well as lower limit. So that will put a limit on how much gains you have. If you have higher gain, then the reference as well as the control voltage can become high value, like a very high value. And then the op-amp might get saturated, which is not considered in the simulation as of now. But yeah, these are the practical issues.
Understood, sir. And just one more question, sir.
Yeah.
In assignments, it is given like, or rather, the terminology that is used is approximate models. Does
Yes.
approximate model mean practical models, or what is exactly that term mean?
So
That
I think
approximate model?
approximate model is what they're meaning, this first order model, because we have considered too many approximations in this or assumptions in this model. So I think this is the approximate model that they are giving, and the others are the more accurate model.
Okay, the first model that we started with, that is
Yes,
the
yes.
approximate model.
Yes.
Okay, fine. Thank you.
And sir has found, or like sir has shown using the switch simulation, that first order model is decently capturing the dynamics, and this is simpler. So we have proceeded with this first order model to design the controller till the bandwidth of FSW by 10. Although these are more accurate, this is like more simplified and easy for us to design the controllers. But it is also required to know about more accurate models. So that's why sir has discussed this. However, you might get a doubt that why sir has used this, because it is sufficient to design the controller and it makes our life simpler. So that's why sir has considered. Although you can also use more accurate models to design the controller.
Yeah, but the calculations will be that much harder.
Yes, yes. So that's why we have chosen that. Okay. So let me quickly summarize what we have discussed in today's problem solving session. We have started with the small signal block diagram of a practical buck converter operating under current mode control, and we have seen that it remains same as of voltage mode control, but the GBC for voltage mode control buck as well as current mode control buck will be different because the control input here is control voltage and here it is the current reference IC perturbation. And then we have seen that we need to first check the accuracy of the model before designing the controller. And for today's discussion, we have considered first order model and two more accurate models using two different methods. And then later we have designed the controller. So the first order model is coming from few approximations, considering few approximations. First approximation being the ripple of the inductor is neglected. And then the second approximation, what is the second approximation? Anyone remembers?
Ramp
Yes, ramp
compensation.
compensation is not considered. And then considering the inductor current is constant because ripple is not there, we get this transfer function. This is for ideal. We can also do the same for practical, and these are the poles and zeros as well as the DC gains that we got for both the cases. And then we have seen that here we have considered few approximations, and that's why it is approximated first order model. But if we want to go for more accurate small signal model, then we have to consider the ramp approximation as well as the ripple. So in the first case, we have calculated the average by assuming the average during dt as well as average during 1 minus dt is same. So we got the average of IL expression, and then we have perturbed and ignored the second order terms and removed the DC terms because we are doing AC analysis, and then we can obtain this expression. After substituting M1 perturb, we can get the generic expression in terms of V in and V naught, where FM, K1 and K2 expressions can be obtained like this. If you go for method 2, where we assume that the average on the left side as well as average on the right side are not equal, now this is more generic compared to method 1. So in that case, we have calculated the average during the dt region, average during the 1 minus dt region, and then calculated the overall average. So because of this, we'll get second order terms. Now we have to differentiate it and linearize it and make it a linear model. So after doing that, we simplified it to get this final expression. Now for a buck converter, we know M1 and M2. So substituting the M1 perturb as well as M2 perturb, we can get the generalized expression in terms of F1, K1 and K2. So now just to quickly summarize between method 1 and method 2, these are the FMs, these are the K1s and these are the K2s. Maybe I should also put the generic expression. So this is the generic expression. So if, so this is the generic expression. And these are the gains as well as, three gains for both methods, method 1 and method 2. Then we have started solving one problem where I have considered an ideal buck converter, and I have asked you to calculate the steady state as well as poles and zeros, which we have discussed at the beginning of the session. And then we have seen that PI controller is enough for this because there is no ESR 0. And then by doing stable pole zero cancellation and targeting a bandwidth of 1/10 of the switching frequency, which was again given in the question, we have obtained the gains, and then we have seen the phase margin is 90 degrees. Now, in order to make it more generic, we have considered a practical buck converter, and then we have calculated the poles and zeros to obtain the control to output transfer function. And then in this case, because of the additional ESR 0, we need additional pole in the controller, which will make us go for a type 2 compensator. Now doing stable pole zero cancellation and then targeting a bandwidth of FC, we got the generic terms for all the three gains. In the question, it is given 1/10 of the switching frequency. So considering that bandwidth, we have obtained the controller transfer function. But if you see, if this pole is pushed further away from the imaginary axis, and say if it is neglected as it is too far, then it will become PA controller, and also in this case, the phase number is 90. So if you have any questions, you can ask us. I'll end this session here. Any questions?
No, sir. Thank you.
Okay. Thank you for joining, and I wish you all the best for your weekend problem solving session. I'll meet you again in weekend problem solving session. Okay, then good night, everyone. See you in the next session.
Thank you, sir. Good night.
Thank you. Thank you.